recharge structures in urban areas. The rainfall runoff in urban areas would usually be much more than in agricultural lands or in forest lands. That is because in the urban areas we have a good amount of built up areas. Either we say the paved roads or the built up structures and the various other usages in the urban areas would not facilitate the recharge to groundwater. Open areas within the house premises or open areas in compounds, in office compounds or playgrounds, and unpaved roads would contribute for recharge. Since the recharge component to groundwater is restricted on account of the various land uses which will not permit the recharge, it is required to construct adequate recharge structures to facilitate recharge to groundwater. We will now discuss how such structures can be constructed within the premises of a building, and also how such structures can be constructed in open grounds and in big areas draining something like 5 to 10 hectares of land. The design given for such recharge pits is something like what is shown here. A trench will be excavated within the house premises of a suitable size, suitable width and length, and such a trench would be filled with big stone at the bottom and small stone, what we call metal, at the top of the big stone, and finally a layer of sand. The runoff water coming from the rooftop or the open areas within the premises would enter like this, and it will seep through, percolate down below and goes further down to recharge the groundwater table. Now in this case, this is something like a filter bed design. We have sand which is supported by a coarser metal and in turn supported by a bigger stone. This is a slow sand filter bed. In this slow sand filter bed, the turbid water or raw water coming from the rooftop and the open areas gets filtered, and filtered water comes out. Now let us see this design for the purpose of recharge. If the water has got to go down to recharge the water table down below, is there a need for filtering that water? The bowels of earth does the function of filtering. We see in the case of any stored water body, even if it is turbid, like the runoff water in a tank, though it is turbid, the groundwater in the wells down below is quite clear. That means the turbid water gets filtered in the bowels of earth and travels to recharge the water table, and it appears as clear water under the water table conditions. So for recharging to water table, there is no necessity to filter through a medium like this. If supposing we want to collect that water and then store it for future use, domestic use or gardening, then it is required to take it through a filter like this and collect the filtered water. But if it is intended for recharge in the water table, such a filter is not required. There is one problem with a filter of this type with regard to the rates of infiltration. The amount of infiltration rate per square meter of the bed, if supposing it is 0.5 liters or 0.3 liters per square meter per second, then even if we construct a bed of 5 meters length, then it works out to about 1.5 liters per second or 2.5 liters per second as infiltration rate, assuming that the soils are capable of taking that infiltration rate coming through the sandy bed. Still, the amount of infiltration that can take place in the sandy bed is of the order of about 2 liters per second in a trench having 5 meters length. Now, the rate of inflow in a 200 square meters plot would be of a dimension varying from 10 liters per second to 20 liters per second. When that is the rate of inflow and the rate of infiltration is so much less, what would happen to the amount of inflow? It finds a way out. Water will overflow this sandy bed and goes into the street. So, the rate at which the water enters the pit would be much higher for ordinary precipitation of 1 inch per hour, and most of it would go over the pit because the infiltration rate is limited by the design of the filter bed. Now, let us see if there is a better design or an appropriate design to take care of the rate of inflow, and also whether a design which is costing less than a filter bed is possible. This we will study in the next sketch. In this sketch, an alternative design has been given for collecting the rainwater occurring as runoff within the house premises. Let us see this sectional view. This would be the trench, and the inflow from the premises comes like this, and it will have a small silt trap. The silt, if at all, if there is any silt, it will get deposited here and it will overflow and gets collected here. This is just a collection trench, and in order to retain the sides of the trench, rough stone dry packing can be done, something like a revetment, a vertical rough stone dry packing. If the soils are loose, it can be even having slight slope, and there is no revetment at the bottom. This revetment is only intended to hold the soils so that it may not cave into the trench, because this is an open trench, and the trench is covered by a perforated RC jali, which is something similar to a ventilator with appropriate reinforcement, so that even a child or a person standing on this would not result in a failure of the jali. This jali is intended primarily for preventing people or children falling into the trench, and the water that overflows here from the silt trap would flow into the holes of the jali and gets collected here. This can be at a distance of about 1 meter from the compound wall, and even if the main building is very close by, the foundations of that building wall or the column of the building would be taken down, and it will always be lower than this level. And because this is a shallow depth of 1 meter, and the foundations will be usually taken to more than 1 meter depth foundation of column or any such thing. A cavity of this type would not interfere with the foundations of a building. The foundations of the column should not have any cavity within that bulb of pressure zone, what we call bulb of pressure zone. So now this cavity is not in the bulb of pressure zone of the foundation, it is away from the foundation and it is at a higher level than the foundation level. So there is no problem of interfering with the foundations and causing instability with regard to the structural details of the foundation. And when we see this in the plan, this is something like this. We have rough stone revetment all round of 0.225 meter thick, and this is the RC jali, and this is the silt trap. Water flowing like this will fill this one and overflow into this and flows through the jali holes to fill up this. Now a trench of 2 meter length should be provided for every 100 square meter of plot area. That is, for a precipitation of 1 inch per hour, this would be adequate. The silt trap may have some silt now and then. Once in a few months it may have to be removed if it is silted up, and that silt can be used for gardening, and that's be a good thing, because otherwise the silt will enter into this pit and gets collected here. And during continuous very heavy rains there may be overflow, but that would be only a rare occasion when this gets filled up and then it overflows. Otherwise this will intercept and store water that comes out of a 1 inch precipitation in 1 hour, and again it seeps through. For places like Hyderabad and red soil areas, urban areas, the seepage would be quite significant and the water will disappear after a few hours. Then for every 10 hectares of open land or built up area, we require a device for recharging the groundwater. For example, there will be streets and open areas, and rainfall occurring in the streets as well as in the open areas like playgrounds or big office compounds or any other area of public utility. The runoff will be flowing in the streets, and such runoff also has got to be collected and stored in a recharge pit of adequate size. We will now deal with that in the next sketch. This size in the plan, and as shown in the section, 22 meters width and 22 meters length at the top and 16 meters by 16 meters at the bottom can be constructed. Let us say this is the ground level and this is the ground level. Water drained from about 10 hectares of land enters here. This is a silt trap, and it overflows and comes into this pit. Just a surface flow. There is no grating, nothing of that sort. This is just an open pit, like what we see the pits at temples, what we call temple tanks, something like that. 22 meters in length and 22 meters in width, 22 meters square area will have to be found for locating such pit. And the pit can be given a side slope of half to 1 on either side, and this portion has got to be riveted with rough stone of 0.225 thick. This rough stone will not prevent seepage of flow. It is a dry packing. There is no cement used. It is just a rough stone dry packing facilitating the water to seep through. Even in the premises, in the house premises also, the rough stone used is just dry and without cement. So therefore, it is possible that water can seep through without any hindrance. The purpose of this revetment is to retain the sides, otherwise the sides may collapse and it will silt up here, reducing the capacity of the pit. Because the water flows here, there is a need for having a small apron. Otherwise, water falling like this will create a scour here. So in the beginning, when there is no water in this pit, when water collects in the silt trap and overflows, it would cause erosion here unless this apron for a small length is provided. Now as the water level rises, it will fill up this, and even this will get filled up at the time of very heavy rains, and an overflow has got to be provided. This overflow goes into a drain, and such drains collect in a natural wagu, natural stream, and the natural stream can have a minor irrigation structure, a tank-like structure, which will in turn facilitate a recharge to water table. So there are three stages. One is the recharge structure within the premises. The second thing is a recharge structure of a much bigger size, 22 meter by 22 meter, for recharging water coming from an area of 10 hectares, which includes the roads and all the open grounds, and ultimately a tank storage structure, a minor irrigation tank storage structure similar to that across a stream. And these tanks will have to be maintained properly and have to be designed also properly to carry these flows coming out of such pits. Let us see how this looks in a plan. This is the bottom of the pit, which is 16 meter by 16 meter, and this is the top of the pit in plan, which is 22 meter by 22 meter, and this is the silt trap. Water enters here and flows down, and this is that apron which I was telling, and it fills up. Now a question may come up: is there space in an urban area to provide for construction of such a pit? There are several areas available in the shape of compounds of big offices, or could be some open areas in parks and playgrounds. And if there is a problem to find out a space for this, I feel that the area has got to be acquired, just as we acquire for increasing the width of the road. So we may have to acquire for accommodating a pit of this type in a 5 hectare area. When we do all these works, that is the house premises recharge as well as the public places recharge for every 5 hectares, and again a minor irrigation tank down below, then the amount of rainfall that is intercepted and allowed to go for recharge to groundwater would become quite significant. In fact, the water table level in an urban area can come up to a few meters below ground level, like 2 meters below ground level, and the required groundwater can be tapped even through open dug wells, as was done much earlier, a century back. And enough of groundwater would then be available to meet the requirements of the urban population, and minimum treatment is needed, like disinfection, chlorination and supply. The capital cost of works also would get reduced, because in any given situation in urban area we have nearly 600 to 800 mm of rainfall per year, and considering that even about 1/3 of it goes for recharge to groundwater in the urban area, there is no need to get water from anywhere else, from any stream nearby or any faraway place, because the groundwater itself will be able to supply for the drinking water requirements. Actually, in urban area, the groundwater recharge is able to support agricultural operations. And we all know that the quantity of water used for agriculture in a rural area is nearly 95% of the total water used, and it's only 5% of groundwater that is used for domestic purposes, for drinking water. Now, in this case of an urban area, we don't have agricultural use. All that water is available for domestic purposes, and it is possible to get the requirements of the urban area water supply or domestic water supply through such recharge devices and through groundwater. Even in the urban areas, there may be a need for having subsurface dams along the stream courses down below the tanks in order to prevent the flow of groundwater to a lower area. So the urban water, drinking water or domestic water requirements can be totally met through such recharge structures, and therefore adequate importance will have to be given for these three types of structures. One is recharge structure in the house premises. The second one is the recharge structure in the public places, and the third one is a tank structure in the streams.